there anybody that did not pick up the review sheet on the way in? If you look at that, you will see that it is optional. So
I wasn't able to read it last night.
we're not collecting it. I don't want it. But it's for ready? Okay, it's optional. It's for review in preparation for Friday's quiz. As we go through today's presentation, there's going to be a number of those problems that we'll do together. A little bit of everything. There's a lot of information on here. I'm going to go through it fairly quickly. If you have questions along the way, by all means, please ask. But unless you tell me to slow down or raise a hand with a question, I'm just going to keep plugging away. I would appreciate it if you haven't already, if you'd put your phones away, because if you're texting me to ask me questions, I won't be looking at my phone to answer. So let's get busy. All right, on the back of your sheet, we got a bunch of matching terms. That's the first thing we're going to hit, is the terminology. We got solvents, solutes, solutions, and a whole bunch of other stuff. So solute is simply the stuff that gets dissolved in the solvent. If you're making Kool-Aid, you're making Gatorade, you put the powder in the powder is your solute. The water would be your solvent. Water is typically the solvent, it doesn't have to be the solvent. If you dissolve something else in alcohol, then alcohol is going to be your solvent. The solution is what you get as a result of dissolving your solute in your solvent, and it should be homogeneous or it's not a solution. So it's all going to be mixed evenly. It's going to be the same color throughout. You're not going to be able to see little particles, floaties, nothing like that. Just one homogeneous solution. If we are dissolving, if we're making an aqueous solution, then it doesn't matter what there's more of. Water is always going to be the solvent for an aqueous solution. But if we're mixing two solutions or two liquids that are not water, then whichever one there is more of is going to be your solvent, and whichever liquid there's less of would be considered your solute. If something is soluble, it dissolves. Something might be soluble in water, but it might not be soluble in something else. For example, salt dissolves pretty readily in water, but salt will not dissolve in acetone, which is your nail polish remover. Styrofoam will not dissolve in water, but if you put styrofoam in acetone, it just kind of melts and bubbles and end up with a slimy ooze that forms at the bottom, and it doesn't look anything like styrofoam anymore. Solubility is a measure of how much we can dissolve in a solvent, how much solute can be dissolved in a solvent. We'll look at a solubility table in just a moment. Bless you. And miscible and immiscible are like possible and impossible. If two liquids are miscible, they will mix. And if they're immiscible, they won't mix, like oil and water. Something is possible, it can happen. If something is impossible, it can't happen. Easy peasy? Giddy up. All right. Solubility curve. This is not the solubility curve you have on your sheet, just a generic one that only has two substances on it. We've got sugar and salt. This shows you how much sugar we can dissolve in 100 grams or 100 milliliters of water at a given temperature. So you can see that sugar is very temperature dependent. At low temperatures, you can dissolve maybe about 175 grams of sugar in 100 milliliters of water. At high temperatures, at boiling temperature, you can dissolve almost 3 times that, almost 500 grams of water. Salt, much less temperature dependent, but that just tells you how much of a solution, how much of a solute you can dissolve in 100 grams or 100 milliliters of water. If the value is right on the line, then the solution is saturated, which means we've dissolved as much as we can. If we're talking about something under here, if we're talking about 150 grams of sugar at any temperature, that solution is going to be unsaturated, which means we could dissolve a little more water or a little more sugar in there. And if it's above the line, then it's supersaturated. That's a unique case, but sometimes we can supersaturate a solution. For example, with sugar, if we increase the temperature up to near boiling and maybe dissolve 300 grams and then cool it very gradually, we may be able to keep more sugar dissolved in there than we could normally. This is just another solubility curve that's got a whole bunch of substances on it. I'm just going to move past this because you've got a solubility curve on your sheet, your review sheet. We'll do a couple of questions to review to make sure that we can use that solubility curve. So the first one I want you to check on is how much potassium chlorate can be dissolved in 100 grams of water at 10 degrees Celsius. So I'm going to wait for a moment while you look at the solubility table, which is very small. Find your potassium chlorate curve, find 10 degrees, and then read that table and jot down roughly. It'll be a little bit of an estimate, but it should be a pretty good estimate. How many grams of water or how many grams of potassium chlorate can be dissolved in 100 grams of water at 10 degrees? What you got? Is it a little bit more than that? Yeah. Sure.
Oh, I was looking at the school one. I think Reggie's
Yeah, that's not bad. So, I estimated that to be about 8 grams, maybe about 7 or 6. It's, as I said, it's puny little table, hard to read the numbers, but if you thought it was 25, you've got trouble reading a solubility curve. Next one, a little bit of math, not a lot. What is the minimum volume of water required to dissolve 40 grams of sodium nitrate at 30 degrees Celsius? What to do, what to do? So the ratio of grams of solute per grams of solvent is going to be the same for a given temperature. We have twice as much liquid at a given temperature. We're going to be able to dissolve twice as much solute. So from your table, you should be able to determine how much sodium nitrate can be dissolved in 100 grams of water, which, if you look at it like I look at it, is about 95 grams of sodium nitrate. So for every 100 grams of water, we can get 95 grams of sodium nitrate. So for an unknown volume of water, we can dissolve 40 grams of sodium nitrate. So we just set up a ratio. 100 over 95 is going to be the same as X over 40. And so we multiply both sides by 40, divide by 95, you should get about 42 mils. Sometimes you'll see the solubility tables that'll say 100 grams of water. Sometimes they'll say 100 milliliters of water. Sometimes they'll say 100 cubic centimeters of water. All those units are equivalent. Last one is determining the temperature at which potassium chlorate and sodium chloride will have the same solubility. So those are your two bottom curves. Potassium chlorate is the one that starts the lowest, and eventually, after about 50 or 60 degrees, it curves up and crosses the sodium chloride. We're looking for the point of intersection. At what temperature do those two lines cross? And hopefully you're going to see that that's somewhere between 75 and 80 degrees. I estimated that to be 77. Anyone have questions on where any of those answers came from? It's all good? Okay. Concentrations. Concentration is simply a measure of how much solute is dissolved in... Hold on. Is it you, Em?
Yeah, I can't help it.
Okay, it's fine. We're just going to wait for you to hiccup again.
No.
Yeah?
Continue.
We will. This won't take long.
Yeah, it's gonna. It's probably one away now.
I know. That's what you want, isn't it?
Yeah.
Okay, so we'll just wait for a minute.
That's amazing. I think you're good.
If you want me to stop again, you just hiccup, okay?
Okay.
All right. All right, so here's just some pictures of solutions of different concentrations. This is red dye in water. When it's very diluted, it's barely red, it's a little bit pink. It gets darker and darker and darker as we add more and more of the solute, so it gets more concentrated. Definition of molarity, or the definition, I guess we quantify our concentrations as molarity. Please make sure that when we're calculating molarities, your volumes are always in liters. Molarity is defined as moles per liter, not moles per milliliter. We got our little molarity triangle. Easy little guy to remember. Moles at the peak, and then molarity in liters across the base. To use that triangle, all we do is cover up what we're hunting for. So if we're looking for molarity, we're going to have moles over liters, which is what we have right here. If we are solving for moles, cover that bad boy up, and we'll have molarity times liters. And if we're looking for liters, moles over molarity. So if we look at question number 18, what's the molarity of a 125 milliliter solution that has 1.6 grams of sodium hydroxide dissolved in it? We are looking for molarity, so we need moles over liters. We don't have moles, we've got grams. We've been doing this for a long time. We certainly know how to convert grams into moles. So we start with our 1.6 grams of sodium hydroxide, convert that into moles. 1 mole for every 40 grams. That's going to give us 0.04 moles. And once we have that, calculating the molarity is going to be a piece of cake, because we've got our friendly little handy-dandy triangle. Our molarity is moles over liters. Again, make sure you use liters. So we're going to have 0.04 divided by 0.125. There are 1,000 milliliters in a liter. So to convert from milliliters to liters, we divide by 1,000. Little pluggage and chuggage, and our molarity is 0.32. 0.32 molar sodium hydroxide solution. That's good? Let me know if I'm flipping too fast. Number 19. Same, only different. Kind of the same problem, but in the opposite direction. So now we're given the molarity and the volume, and we want to find out how many grams it takes to get that solution. So we use our triangle first. Our 6 liters is our volume, multiplied by our molarity of 3 moles per liter. So we need 18 moles of the magnesium chloride. And now that we know how many moles we need, we're simply going to convert our moles into grams. There's 95.3 grams for every 1 mole of magnesium chloride. So 18 times 95 gets us about 1,700. That's fine. Any questions? Okay. Too fast? Good.
No, I just need to know.
Okay. Dilutions of solutions. We introduced this, I think it was last week in large group. I don't remember exactly what day. But when we want to dilute a solution, what happens to the number of moles? Well, all we're doing is adding more water when we dilute. So the amount of stuff in there is going to remain the same. So we start out with a concentrated solution, a whole bunch of solute in a relatively small volume. We add some more water, and now we've got less stuff per volume, but we still have the same amount of stuff. It's just in a bigger volume. So our equation, M1V1 equals M2V2. I've written it with exaggerated symbols. Our concentrated solution is going to have a large molarity for a smaller volume, and when we dilute it, our volume is going to get bigger, but our concentration is going to get smaller because we're watering it down. Those are going to be equal. M1V1 is equal to M2V2. Please just make sure you're keeping track of which M corresponds to which V, and then it's hard to screw this up. So, for number 22, if we have a unknown volume, we're looking for the volume of our 6 molar stock solution. So 6 molar is our concentrated solution. V1 is what we're hunting for. M2 and V2 are both given. We want to make 0.5 molar solution, and we want to make 1,000 milliliters of it. So M1V1 equals M2V2. 6 molar times our unknown velocity is equal volume is equal to 0.5 molar times 1,000 mils. Divide both sides by 6, and you're going to get 83.3 mils. If it's asking for liters, then you simply divide it by 1,000, it'd be 0.083. The only time you really have to convert your volumes into liters is when you're using it to calculate molarity, because your molarity is moles per liter. And we are going. Titration, you did titration on Friday in the lab. Just a process used to determine the concentration of the solution, which is what you did. Same equation. That's pretty neat. That's nice. The only difference is instead of 1s and 2s, we got acids and bases. So the molarity of the acid times the volume of the acid is going to be equal to the molarity of the base times the volume of the base. In your lab, you knew the concentration and the volume of the base. You knew the volume of the acid and you used that to solve for the molarity of the acid. Since molarity times volume is moles per liter times liter, that's going to give you moles. So if we have equal number of moles of our H plus from our acid and our OH minus, we're going to have a neutral solution, which is what we're hunting for. So number 21, what's the concentration of hydrochloric acid? If 22 mils of 0.2 molar sodium hydroxide neutralizes 44 mils of hydrochloric acid. Same guy, just make sure your molarities of your acid and volume of your acid stay together, and base stay together. So 0.2 times 22 equals our unknown volume, our unknown molarity times 44. Little simple algebra, plug and chug, 0.1 molar HCl. This guy should look familiar. For our stoichiometry problems, all we're doing is a combination of our little roadmap that we've been using for the last 3 or 4 months, maybe 5 or 6 months, and our molarity triangle. So problem number 26, we're looking for the volume of a 0.1 molar sodium sulfate solution that's required to produce 25.4 grams of barium sulfate in the reaction that's shown on your sheet. We should write down what we know. It says we got 0.1 molar solution, we got 25.4 grams, and we're hunting for the volume of that 0.1 molar solution. It's already balanced. This is a 1-to-1 mole to mole ratio. So when we convert from moles to moles, that will be a simple trick. So we're starting with 25.4 and we want to work towards our sodium sulfate. So 25.4 is our starting point. We convert that into moles. There's 233.4 grams per mole for barium sulfate. As we just said, there's a 1-to-1 mole ratio. For every 1 mole of sodium sulfate, we're going to get 1 mole of barium sulfate. So that gives us 0.109 moles of sodium sulfate. That's how much of the sodium sulfate we need in terms of moles. But ultimately, we're hunting for volume. So we go back to our triangle. Moles over molarity times volume. So when we cover up our liters, we're going to get moles over molarity. Our moles we just found, 0.109. Molarity was given at the beginning of the problem, 0.1. So that's going to give us 1.09 liters. There it is right there for your viewing pleasure. Hopefully you feel like we're doing a lot of the same stuff we've already done. We're just applying it to a slightly different situation. Haven't heard a peep out of you. Acids and bases. Acids, generally sour. Bases, bitter. We should be able to identify in an equation what's the acid, what's the base, what's the conjugate acid, what's the conjugate base. So the acid is going to be the guy that donates the proton with an H plus ion. The base is going to be the guy that takes the proton. The conjugate acid is going to be what we have after we've accepted that proton. And the conjugate base is going to be what we have after we've given up that proton. So your acid and base are going to be your reactants, your conjugates are going to be your products. So let's have a little look-see at this guy. This one is not on your sheet, I'm afraid, but it's so skinny you could fit that in lots of different places on that sheet. HCl plus H2O yields H3O plus and Cl minus. So in that equation, we want to identify what's the acid, what's the base, what's the conjugate acid, what's the conjugate base. Doesn't matter whether you start on the right-hand side or the left-hand side. Once you can identify one of them, then that makes it a pretty simple trick to identify the other one. And by the process of elimination, you get the other two. So clearly, HCl is losing the H, which gives us Cl minus. So the conjugate base is what we have left after our acid is donated. We should probably recognize HCl as an acid. We've used it a dozen times this year. Water can be either a base or an acid. It depends on what it's mixed with. So HCl we know is an acid, that means water has to be the base. So conjugate acid is what we get after we've picked up the proton. So the base is going to become the conjugate acid. The acid is going to become the conjugate base. The conjugate base, again, is what we have left over after we've lost the proton. So Cl minus has lost the H plus. H2O becomes H3O. And because that proton has positive charge, we also have the positive charge on the H3O. In the next example, it might not be obvious whether NH3 is an acid or a base, and water is going to be the other one. But we have NH3 here and NH4 over here, so clearly the NH4 has picked up the proton. What's the proton acceptor? The base is the proton acceptor. So NH3 picks up that proton, so NH3 has to be the base, which means water this time is going to be our acid. The acid is the proton donor, so H2O is giving up the hydrogen. You start out with 2 H's and an O, you end up with 1 H and an O. Because it's a positive charge that's lost, we go from neutral to negative. In problem number 5 on your review sheet, A through C ask you to identify the conjugate base for each of the acids, and D through F ask you to identify the conjugate acid for each of the bases. To get your conjugate base, that's what's left after you lose a hydrogen. So for each of those three, all you're going to do is take an H off of that original formula, and if it's neutral, you're losing a positive ion, so your new formula, your conjugate base, will have one less positive charge, or typically a negative charge. And your conjugate acids are picking up a positive charge, so if they were neutral, they're going to become positive. If they were negative, they're going to move up to neutral. So are these bases, acids, HBr, that's one of our strong acids, hydrobromic acid, so that's going to be a proton donor. This negative sign is a big clue, but it's a base because it's looking, bases are proton acceptors. So if it's negatively charged, it's certainly going to be attracted to a positively charged proton. And water, as we just saw in the previous slide, can go either way. If it's mixed with a base, it's going to act as an acid. If it's mixed with an acid, it's going to act as a base. We're actually pretty close to done here. Here's our pH scale. There is going to be a couple of items on Friday's quiz where you should be able to identify whether it's acidic or basic and relatively where on the scale it's going to be. Yeah.
How are we supposed to know that? Like where it's
Um,
supposed to be?
Well, most of them we've given you as examples.
So we have to
So
have
like,
this memorized?
I don't know that you necessarily need to memorize them, but you should certainly familiarize yourself with some of them. All of your household cleaners,
Is
basic. Your acids are obviously acidic. Sodas are going to be acidic. Juices are going to be acidic. Virtually everything that we ingest
What about like?
is acidic. Water. So, water is neutral. Blood is just a little bit dicey because it has a range from 6 to about 8.5. I think generally it's considered basic. What do we got here? Yeah, on the answer key here, we've got blood at about 7.5.
So would that be before or after?
That would be basic, so that would be after,
So it'd be,
So blood would be basic.
yes. Sour things generally don't taste bad, and if they're not very acidic, they're really not going to taste very sour. But as a general rule, we don't like bitter stuff. Unless, well, yeah, as a general rule, most people don't like bitter flavored things like soap. So there's very few basic items that we purposefully put into our bodies. All right, we talked a little bit about titration earlier. Showed you the MAVA equals MBVB equation. Indicator is just another term that you should recognize. The indicator is the dye that you use when you're doing a titration to find that equivalence point. In the lab you did on Friday, it was the phenolphthalein, which when you neutralize the solution, turned a bright pink. The equivalence point is where the concentrations of the two ions are equal. So that's when our pH is going to be equal to 7. This problem you do not have on your review sheet. I think it would be worthwhile to find a little spot, maybe under your little chemistry icon. You probably have room for it. It's not going to take up a lot of space. Again, we're given a mass of sodium bicarbonate. So that's a known value. 28.35 mils of hydrochloric acid. That's a known volume. And we are looking for molarity. So under your balanced chemical equation, jot down what we know, what we're hunting for. So we're looking for the molarity of the HCl. We have 0.263 grams of sodium bicarb to start with. I didn't include it here, but we certainly could write 28.35 mils under the HCl as well. And then I would encourage you, if you haven't already, but sketch out that little map like you probably have done for 4 or 5 other tests with your grams to moles and particles to moles and moles to liters and then moles to moles with 3 legs coming off of there again, just as a little concept map to figure out where you're at and where you need to be. So we're starting out with 0.263 grams of sodium bicarb. The only way we can relate our sodium bicarb to our HCl is through moles. So we're going to have to convert our grams to moles. There are 106 grams per mole for sodium bicarb. This equation is already balanced for you. So there's 2 moles of HCl for every 1 mole of sodium bicarb. Bless you. That tells us how many moles of HCl we have. And ultimately we're looking for molarity. From our little triangle, we know that molarity is moles per liter. Well, we're given the liters. If we can figure out the moles, then we just take our moles and divide it by liters, not milliliters, but liters, and we're done so. So we got 0.00496 moles of hydrochloric acid. We're going to divide that by our volume of hydrochloric acid, which is 0.02835. Convert your milliliters into liters, and it's game over. Sound good? All right, the only thing we have left is a little bit about pH calculations and pH equations. These equations are the same equations that you have in the upper right-hand corner of your equation or your review sheet. Those are going to be provided for you on Friday. This is really not an equation, but just a little reminder that on that pH scale, it's a logarithmic scale. So if you go from pH of 4 to a pH of 3, your solution is going to be 10 times as acidic. And then to go from 3 to 2 is another 10 times as acidic, which means our concentration of H plus ions is increasing by a factor of 10 for every jump of 1 unit on the pH scale. Our pH equation and pOH equation are the same. The only thing that's different is whether it's the concentration of the hydrogen ion or the hydroxide ion, and then go in the opposite direction to find the concentration. We're going to do 10 to the negative pH or 10 to the negative pOH. The only dicey part of that is making sure that you know how to put those into your calculator. So let's do one. Problem number 9 is actually problem number 12, I believe. pH of sulfuric acid with a concentration of 0.00394. Depending on which calculator you have, what I'm describing for how to enter it may be a little bit different. This guy is pretty popular. A lot of you have this guy. This one allows you just hit the negative and then the log button. It'll open up a parentheses and then you just plug in your concentration value, hit enter. Works like $1 million. Other calculators, you have to put in the concentration and then hit the log. If it doesn't allow you to hit the negative log, then it's going to give you a negative value for your pH, but then you have to recognize that your pH is actually positive. So one way or another, you should be able to get 2.4 for this concentration. If you have any difficulty in getting that on your calculator, please let us know in just a minute. We've got one more problem after this and we're done. Last one. Going the other way. Seawater has a pH of 8.5. pH is related to hydrogen ions. So since it's giving us pH and asking for hydrogen, we don't have to worry about the POH plus pH equals 14. We can just go directly from our pH to our concentration. But in some of the problems on your worksheet, it gave you the pH and then it asked you for the concentration of the hydroxide ion. So you find the concentration and then you do your 14 minus and that'll give you your new concentration. All right, so we want 10 to the negative 8.5. You might have to use 1 times 10 to the negative 8.5. If you're using your calculator, please use your EE button or your EXP button rather than hitting a whole bunch of extra buttons. But one way or another, you should be able to get 3.16 times 10 to the negative 9. There's 3 zeros, 3 more zeros, and 3 more places before we get that non-zero in front of the decimal. So final answer should be 3.16 times 10 to the negative 9 molar is the concentration of hydrogen ions. And that, chemistry kids, is the end of the show. So you've got 12 minutes to